Welcome! In this session, we'll explore LeetCode problem number 1650, lowest common ancestor of a binary tree 3. This is a fascinating problem that challenges us to find the lowest common ancestor of two nodes in a binary tree where each node has a parent pointer. Let's dive in and uncover the solution together. In this problem, we are tasked with finding the lowest common ancestor, or LCA, of two nodes in a binary tree. Each node in the tree has a reference to its parent node, which allows us to traverse upward in the tree. The lowest common ancestor of two nodes, P and Q, is the lowest node in the tree that is an ancestor of both P and Q. Importantly, a node is considered a descendant of itself, so if P and Q are the same node, the LCA is simply P, or equivalently, Q. For the input, we are given two nodes, P and Q, each with a value and a reference to their parent. The output is the node that represents their lowest common ancestor. Let's now look at some examples to better understand this concept. In our first example, we are working with the binary tree shown. Here, P is the node with the value 5, and Q is the node with the value 1. The lowest common ancestor of nodes 5 and 1 is the node with the value 3. This is because node 3 is the lowest node in the tree that has both 5 and 1 as its descendants. Notice that node 3 is the root of the tree, and both P and Q are located in separate subtrees stemming from it. Therefore, node 3 is the correct answer for this example. Now in the second example, we use the same binary tree, but this time P is the node with the value 5, and Q is the node with the value 4. The lowest common ancestor here is the node with the value 5. This is because node 5 is the direct ancestor of node 4, and as per the definition, a node is considered a descendant of itself. Therefore, in situations like this where one node is an ancestor of the other, the ancestor node itself is the LCA. In the third example, we again use the same tree, but now P is the node with the value 7, and Q is the node with the value 4. The lowest common ancestor in this case is the node with the value 2. If you look at the tree, node 2 is the parent of both nodes 7 and 4, making it the lowest node that has both nodes as descendants. This demonstrates that the LCA does not always have to be the root node or one of the input nodes, it can be any node that satisfies the conditions. Finally, let's review the constraints and edge cases. The tree can have up to 100,000 nodes, and each node's value is guaranteed to be unique, ranging from -1 billion to +1 billion. Additionally, both P and Q are guaranteed to exist in the tree, which simplifies the problem since we don't have to handle cases where nodes are missing. Some important edge cases include scenarios where P and Q are the same node, in which case the LCA is the node itself. Similarly, if P is the parent of Q, the LCA is P, and if Q is the parent of P, the LCA is Q. The solution must also handle both balanced and unbalanced trees efficiently, ensuring robustness across different tree structures. To solve this problem, we need to identify the lowest common ancestor, or LCA, of two nodes in a binary tree where each node has a reference to its parent. This parent pointer simplifies the process, as it allows us to traverse upwards from any node directly to its ancestors. One approach we could use is the brute force method, which involves storing the ancestral paths for both nodes. Here's the intuition: as we traverse upwards from each node, we record the path of ancestors in a list. Once we have the lists for both nodes, we compare them to find the first common ancestor. While this method is straightforward, it has significant drawbacks. Traversing each node to the root takes O(h) time, and comparing the two lists in a nested loop results in O(h²) time complexity in the worst case. Additionally, the space requirements for storing paths make it inefficient for larger trees. Another alternative is the optimized two-pointer technique, which avoids storing paths altogether. Instead, we use two pointers to traverse upwards from each node. When a pointer reaches the root, it switches to the other node's starting point. This ensures both pointers traverse the same distance, eventually meeting at the LCA. This insight significantly reduces complexity and inefficiency. To implement the two-pointer technique, we begin by initializing two pointers, one starting at node P and the other at node Q. Next, we move each pointer upwards through their respective parent pointers. If a pointer reaches null, indicating that it has traversed to the root, we redirect it to the other node's starting position. This ensures both pointers traverse the same total distance, regardless of the initial depth of their starting nodes. The process continues until the pointers meet, and this meeting point is guaranteed to be the lowest common ancestor. The efficiency of this method lies in its minimal time and space complexity. Traversing upwards takes O(h) time, and since no additional data structures are used, the space complexity is O(1). This approach is not only efficient but also simple to implement. Another possible strategy is the recursive approach, which involves traversing upwards using recursive calls. The process stops when the current node matches either P or Q, and recursion depth is used to track the LCA. However, recursion introduces its own challenges, such as potential stack overflow in deep trees, and managing recursion depth can add unnecessary complexity to the solution. Among the approaches considered, the two-pointer technique is the most efficient and practical solution for this problem. It avoids the inefficiencies of the brute force approach, such as redundant comparisons and high memory usage, while maintaining simplicity. By ensuring both pointers traverse equal paths, this method guarantees correctness and reduces the time complexity to O(h), with constant space usage. Compared to the recursive approach, the two-pointer technique is more robust, as it avoids the risk of stack overflow in deep trees and eliminates the need for additional depth management. While the brute force method is intuitive, its O(h²) time complexity and high space requirements make it unsuitable for larger trees. The recursive approach, though elegant, is less practical due to its limitations in deep tree scenarios. The two-pointer technique strikes the perfect balance between efficiency and simplicity, making it the optimal strategy for solving this problem. To solve the problem of finding the lowest common ancestor of two nodes, P and Q, in a binary tree, we can take advantage of the parent pointers that allow us to move upward in the tree. Remember, the lowest common ancestor is the deepest node that is an ancestor of both P and Q. Unlike traditional methods, we don't need to traverse the entire tree downward. Instead, we can trace back from both nodes to their ancestors and determine where their paths intersect. This is similar to finding the intersection point of two linked lists. One key observation is that if both nodes exist in the tree, their ancestor paths will eventually meet. By alternating between P and Q as parent pointers, we can ensure the traversal synchronizes at the LCA. If one node reaches the root while the other doesn't, we simply reset the pointer to the other node, effectively wrapping around to ensure convergence. The algorithm begins by initializing two pointers, A and B, at nodes P and Q, respectively. The traversal works as follows. If pointer A reaches null, meaning it has climbed past the root, it is reset to node Q. Similarly, if pointer B becomes null, it is reset to node P. This process continues until the two pointers meet, at which point they will converge at the lowest common ancestor. Since the tree is finite, this traversal is guaranteed to terminate. The wrapping mechanism ensures that both pointers traverse an equal number of steps, allowing for synchronization. This approach is analogous to how two singly linked lists can intersect at a point, and it guarantees efficiency with a time complexity of O(h) and a constant space usage of O(1). The only data structure we rely on is the parent pointer, which is already part of the tree's structure. There are a few edge cases to consider. First, if P and Q are the same node, the algorithm will correctly identify the node itself as the LCA. Second, if one of the nodes is the root, then the root is naturally the lowest common ancestor. However, if either P or Q does not exist in the tree, the algorithm will still terminate, but the result will not be valid unless additional checks are performed to verify the presence of both nodes. Regarding complexity, the time complexity is O(h), where h is the height of the tree, as the traversal is limited to climbing up the tree. The space complexity remains constant at O(1), since no extra storage is required beyond the two pointers. The pseudocode implementation is straightforward, starting with pointers A and B at P and Q, the while loop continues until they meet, resetting the pointers as needed. Once the pointers converge, the algorithm returns the node at the convergence point. Let's consider an example to see the algorithm in action. Imagine the following binary tree. The root is node 3, with 5 and 1 as its children. Node 5 has children 6 and 2, while node 1 has children 0 and 8. Additionally, node 2 has children 7 and 4. Now, let's find the lowest common ancestor of nodes P equals 5 and Q equals 1. We start by initializing pointer A at node 5 and pointer B at node 1. Both pointers then traverse upward using the parent pointers. pointer A moves from 5 to its parent, 3, while pointer B moves from 1 to its parent, 3. At this point, both pointers point to the same node, 3. Since A equals B, we have found the lowest common ancestor. The final output for this example is that the lowest common ancestor of nodes 5 and 1 is node 3. This result aligns with our expectations, as node 3 is the lowest node in the tree that is an ancestor of both 5 and 1. This example demonstrates the efficiency and simplicity of the algorithm, which leverages parent pointers to solve the problem in O(h) time with minimal space usage. The solution to LeetCode problem number 1650, lowest common ancestor of a binary tree 3, is implemented using an efficient and elegant approach that leverages the parent pointers of the nodes. Here's how the code works step by step. 1. Class definition. The node class is provided, which includes references to its val, left, right, and parent. The parent pointer allows us to traverse upward in the tree. 2. Initialization. In the lowest common ancestor function, two pointers A and B are initialized to the input nodes P and Q. These pointers help us traverse upwards from each node to find their common ancestor. 3. A traversal logic. The while loop runs until A and B meet. In each iteration, if A is not none, it moves to its parent. Otherwise, it resets to Q, the other node. Similarly, if B is not none, it moves to its parent. Otherwise, it resets to P, the other node. This approach ensures that both pointers traverse the same distance by the time they meet, accounting for different depths of the two nodes. For termination, the loop terminates when A equals B, which means the lowest common ancestor is found. This is returned as the result. 5. Efficiency. The algorithm runs in O(h) time complexity, where h is the height of the tree, because each node is visited at most twice. It uses O(1) extra space since no auxiliary data structures are used. This approach elegantly solves the problem by exploiting the parent pointers and ensures that the solution is both time and space efficient. It handles all edge cases, including when one node is the ancestor of the other or when the nodes are at different depths in the tree. Here, we start by defining the node class, which represents the structure of each node in our binary tree. Each node contains a value, references to its left and right children, and a reference to its parent node. The constructor initializes these fields, setting the left, right, and parent references to null by default. Next, we define the solution class, which contains our method to find the lowest common ancestor. The method takes two nodes, P and Q, as input. Inside the method, we initialize two pointers, A and B, to point to P and Q, respectively. The key idea here is to traverse upward in the tree, using the parent references, until the two pointers meet. To achieve this, we use a while loop to continue the traversal as long as A and B are not equal. If A becomes null, we reset it to point to Q, and similarly, if B becomes null, we reset it to point to P. This ensures that both pointers will eventually meet at the lowest common ancestor. At the point where the two pointers meet, we know we have found the lowest common ancestor of the two nodes. This is because the traversal process guarantees that both pointers will eventually reach the same node, regardless of the initial depths of P and Q in the tree. Once the meeting point is identified, we simply return the pointer A, which now points to the lowest common ancestor. This implementation is elegant and efficient, leveraging the parent pointers and requiring no additional memory beyond the two traversal pointers. It ensures that the time complexity is linear, O(n), where n is the number of nodes in the tree, as each pointer traverses at most two full paths in the tree. To solve the problem of finding the lowest common ancestor in a binary tree, let's start with a simple example. Here, we have a binary tree where the root is node 3, with children node 5 and node 1. Node 5 itself has two children, node 6 and node 2. We are tasked with finding the lowest common ancestor of two nodes, P, which is node 5, and Q, which is node 1. The process begins by initializing two pointers, A and B, to start at P and Q respectively. As the algorithm progresses, A moves upwards from node 5 to its parent, node 3, while B moves upwards from node 1 to its parent, node 3. Once both pointers meet at the same node, which is node 3 in this case, we determine that node 3 is the lowest common ancestor. This is the result returned by the algorithm for this example. Now, to better visualize the traversal process, we can break it down into intermediate states. At the first iteration, A points to node 5 and B points to node 1. On the second iteration, A moves to node 3, and B also moves to node 3. At this point, since A and B are pointing to the same node, the algorithm terminates, and we return node 3 as the output. Shifting to another example, consider a scenario where one node is the ancestor of the other. In this tree, node 5 is the parent of node 6. Here, P is node 5, and Q is node 6. Let's explore how the algorithm handles this case. In this example, we start by initializing A to node 5 and B to node 6. As the traversal begins, A remains at node 5 since it's already at the starting node. On the other hand, B moves upwards from node 6 to its parent, which is node 5. Now, both A and B are pointing to the same node, node 5. This means node 5 is the lowest common ancestor. Looking at the intermediate states, during the first iteration, A is at node 5 and B is at node 6. In the second iteration, both A and B are at node 5. The algorithm then concludes, and node 5 is returned as the output. Next, we'll examine a more complex example where the nodes are located at different levels of the tree. Here, the binary tree has an additional level of depth. Node 2, which is a child of node 5, has its own child, node 7. In this scenario, P is node 7, and Q is node 6. The algorithm starts by setting A to node 7 and B to node 6. Initially, A moves from node 7 to its parent, node 2, while B moves from node 6 to its parent, node 5. In the next step, A moves upwards again from node 2 to its parent, node 5, and B remains at node 5. At this point, both A and B are at the same node, node 5. This confirms that node 5 is the lowest common ancestor. Let's take a look at the intermediate states to see how the algorithm reached this conclusion. In the first iteration, A is at node 7, and B is at node 6. By the second iteration, A has moved up to node 2, while B is at node 5. In the third iteration, A moves up again to node 5, and now both A and B are at the same node, node 5. Since the pointers meet, the algorithm terminates and returns node 5 as the output. This demonstrates how the algorithm effectively handles cases where nodes are on different levels of the tree, ensuring we always find the correct lowest common ancestor. To analyze the time complexity of this solution, let's consider the process of pointer traversal. The algorithm uses two pointers, A and B, which start at nodes P and Q, respectively. Both pointers move upwards through the tree, one edge at a time, towards the root. If a pointer reaches the end of its path, meaning the root of the tree, it switches to the other node's starting position. This clever design ensures that each pointer traverses an equal total number of edges, which is the combined height of the two nodes. The algorithm stops when the two pointers meet at their common ancestor. In the worst-case scenario, each pointer may traverse the height of the tree twice, once to reach the root and once to align their paths. Therefore, the maximum traversal is 2h, where h represents the height of the tree. This makes the time complexity O(h). For a balanced binary tree, h is approximately O log n, while for a skewed tree, it can be as large as O(n). Now, let's discuss the space complexity. The memory usage of the algorithm is quite minimal. It uses only two pointers, A and B, for traversal. These pointers do not require any additional memory that depends on the size of the tree. Importantly, the algorithm does not employ auxiliary data structures like stacks or queues to store nodes or intermediate results. As a result, the space complexity is constant, or O(1). Next, let's break this analysis down further into best, average, and worst cases. In the best case, where P and Q are the same node, the algorithm terminates instantly, requiring just O(1) time. For the average case, which typically occurs in a balanced binary tree, the traversal will take around O log n time since the height of the tree is logarithmic in relation to the number of nodes. In the worst case, which happens in a completely unbalanced tree such as a linked list, the traversal time grows to O(n), as the height of the tree equals the total number of nodes. Finally, let's compare this optimized approach to a naive solution. A brute force method might involve traversing the tree from the root, recording the entire paths to both nodes, and then comparing these paths to determine the last common node. This method requires additional space to store the paths and would take time proportional to the size of the tree, resulting in O, and time and space complexity. In contrast, the current optimized approach eliminates the need to store paths altogether. It directly determines the lowest common ancestor in O, H, time and O, 1, space, making it significantly more efficient and scalable. To validate this mathematically, we can see that the time complexity is indeed O, H, as each pointer traverses at most 2 H edges, where H is the height of the tree. The space complexity remains O, 1, because the algorithm uses a constant number of pointers, and this memory usage does not scale with the size of the tree. When solving this problem, there are several common mistakes to watch out for. First, failing to account for the parent pointer during traversal is a major error. Unlike many lowest common ancestor problems, this one provides a parent pointer for each node, and ignoring it can result in overly complex and redundant solutions. By not leveraging this key feature, you end up performing unnecessary computations. Another common pitfall is assuming the tree is always balanced. Binary trees in this problem are not guaranteed to be balanced, so solutions that rely on balance, such as assuming equal depths or symmetrical paths, may fail when the tree is skewed or unbalanced. Lastly, edge cases like one node being an ancestor of the other, or when both nodes are the same, are often overlooked. Forgetting to handle these scenarios can lead to incorrect results or even runtime errors, so it's crucial to consider them when designing your solution. Another challenge arises with inefficient traversal loops. Using nested loops to find paths to the root for both nodes might seem straightforward, but it significantly impacts time complexity. While it works, it's far from optimal and can be streamlined with a two-pointer approach. Similarly, not using a set or similar mechanism to track visited nodes during traversal is another inefficiency. This oversight can cause the same paths to be traversed multiple times, unnecessarily increasing runtime complexity. A key insight for this problem is recognizing its similarity to finding the intersection point of two linked lists. Since each node has a parent pointer, the path to the root can be visualized as a linked list. By utilizing two pointers to traverse these paths, the solution becomes efficient, with a time complexity of O, H, where H is the height of the tree. It's also important to clarify edge cases during an interview, such as whether the nodes are guaranteed to belong to the same tree or if null nodes are possible. A helpful analogy is thinking of this as finding the youngest common ancestor in a family tree, where each person has a direct parent. This problem has connections to several related problems, which can provide additional practice and insights. For example, LeetCode 236, lowest common ancestor of a binary tree, is a variation where nodes don't have parent pointers, requiring a different approach. LeetCode 160, intersection of two linked lists, is another related problem that uses the same concept of finding an intersection point using two pointers. Similarly, LeetCode 1123, lowest common ancestor of deepest leaves, involves finding the LCA of the deepest nodes in a binary tree, which is conceptually adjacent to this problem. Finally, LeetCode 1485, clone a binary tree with random pointers, is another problem involving parent pointers and complex tree traversal. Exploring these problems can deepen your understanding of similar concepts and techniques. There are multiple approaches to solving this problem, each with its own trade-offs. The naive approach involves traversing the path from each node to the root, storing these paths in lists, and then comparing the lists to find the LCA. While simple to implement, this method requires O, H, space, as it stores the paths explicitly. A more optimized solution is the two-pointer approach. By using two pointers to traverse the paths to the root, and redirecting each pointer to the other node's path when it reaches the root, you can reduce both time complexity to O, H, and space complexity to O, 1. This makes it the most efficient solution. Another option is the recursive approach, which involves recursively traversing upward using the parent pointers. While this approach is elegant and intuitive, it can come with additional function call overhead. Each method has its merits, but the two-pointer approach is generally preferred for its efficiency and simplicity. Great job! To wrap up, we summarized the solution to LeetCode problem number 1650, highlighting its time and space complexities. The key takeaway is understanding parent pointers and applying intersection techniques from linked lists. Thank you so much for tuning in. Don't forget to like, subscribe, and keep practicing. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!